Welcome back to Rapid Office Hours. We're talking about dot product today. I'm going to limit it to looking at it in R2 because R2 is kind of nice. It's the board, it's two-dimensional space, we can kind of visualize things, so on. Okay, so how do I do the dot product in general? Now, the dot product, I mean, it's a special case of what's called an inner product. You'll get to that much later on. Inner products are kind of what make a lot of the world go round in a lot of weird ways. Okay, but we're just going to start here with the dot product and we're going to figure out what in the world are we talking about. Okay, so in general, what is it? Well, if you give me a vector u, which looks like u1, u2, okay, and you give me a vector v, which looks like v1, v2, then how do I get the dot product of the two? Now, there are a lot of ways to denote this. I personally don't like this notation, okay, so you just do u and then a big dot, and then v, it's kind of pretty self-explanatory. It's a dot product, whatever. I don't really like doing it that way. I'll explain in later videos where I use a different notation once we introduce like the transpose of a vector and things like that. I think that's a little bit more, I don't know, mathematically rigorous and more applicable in a lot of settings, but this is completely fine for our purposes right now. So how do I do u dotted with v? Here's the game. I go to the component for u in the first part, in the first coordinate, and then I go for the coordinate of v in the first coordinate. I multiply them, and then I do that by multiplying the corresponding coordinates and then just adding along the way. So I'm going to get u1, v1, so u1, v1, and then I move to the next coordinate, u2, v2. Okay, u2, v2. Now, if I wanted to say the dot product in general, in Rn, then I would just go coordinate by coordinate all the way down and just keep adding until I run out of coordinates to do this for. Okay? So for example, how would this work? If I've got u is equal to that, so I'm going to say 1 minus 2 dotted with 3, 5. Okay, what is my rule? It says multiply the first coordinate, so 1 times 3 is 3, plus second coordinates, negative 2 times 5. And that's minus 10. What is 3 plus negative 10? That's 3 minus 10. That's minus 7. Okay, and that's it. All right, that's it for dot products. It's actually a very simple operation. The question that you should be asking, though, is like, why? Why do I care about this at all? Okay, well, here's a special case. Okay, here's a special case. So the special case is, look, what if I do u dotted with itself? What do I get? Okay, well, u dotted with itself gives me what? Corresponding to the rule, let's say u is general up here. That's u1 squared, u2 squared. So that'll be u1 squared plus u2 squared. Okay, and that's very close to this thing, okay, the square root of u1 squared plus u2 squared. I need to square that to eliminate the square root, okay? And this quantity is very special. And it's got a million different names. So this is called the norm of u. Otherwise, other names for it would be the magnitude, the length. I mean, there's all sorts of different things that we can talk about with this particular thing. It has a notation, so it's double vertical bars, and then the vector u, and then double vertical bars. That's what the square root part is, so I'm squaring that, so this square is that thing there. Okay, so what I'm really saying is that the norm of u is the square root of u1 squared plus u2 squared. Why do we call it the norm, the length, the magnitude, all of that? It's because if I draw the vector u, so if here's u, okay, so that's u1, u2, then if I drop that down, and I look at this as u1 and this is u2, and that makes a right triangle, and the Pythagorean theorem tells me that the length of u, okay, so how long is this vector, is going to be the square root of u1 squared plus u2 squared, which I denote by the norm of u. Okay, so these two vertical bars of u. So that's where that comes from. So at the end of the day, why is the dot product useful? Well, it allows me to compute the norm of u as simply the square root of u dotted with itself. Okay? That's one use for the dot product. The dot product has a ton of different uses. We're going to find that the dot product allows us to tell when are two vectors orthogonal to each other. So mostly orthogonal means that they're perpendicular in some ways. I mean, if u is the zero vector, it's a little different. But when are two vectors perpendicular to each other? The dot product will tell us when that's true. The dot product will also be able to tell us in a more advanced context. So like, for example, noise canceling headphones. Okay, so like how do those work? Will they cancel out the waveforms in terms of the different sounds? It turns out that dot products are intimately connected with that, okay? So this is just kind of the start of that entire journey of getting to that place, all right? So hopefully this helps you understand what dot products are in R2. Again, this generalizes to any Rn whatsoever. All of these definitions are the same. You just have more and more components, all right? All right, like, subscribe, all the things, you know what to do. And please ask me questions, okay? Comment down below, ask me questions. I'm happy to work out examples.